Hello there, math and physics students. This is Dr. John. I am your professor today, helping you with pulley problems. This is the last in our pulley problems in this section, where we're going to walk through a little bit more complicated pulley problem. We have three masses, M1 at 10 kilograms, M2 at 80 kilograms, M3 at 25 kilograms, two tensions. Hopefully this yellow here stands out. Tension 1 and tension 2, they may be different, they may be the same. And we have friction. So between this M2 and the table is a coefficient of friction of 0.1. We're not worried about static friction or kinetic friction. We're not worried about significant figures as much in this problem. We're just worried about how do you solve something with two pulleys, three weights, and friction. We're going to do that in much the same way as we have done the other problems, and that is by starting off with this extremely important step of assuming an acceleration. Now in this one case where we have friction, we have to be extremely careful to make sure we get the direction of the motion right, because everything will not autocorrect. It'll give you probably a negative answer for the acceleration if you're wrong, but you're going to have to go back then and redo the whole thing over again. Because what happens with friction is, you have to assume a direction of motion to determine a direction of friction. That's not going to correct if you get a negative answer for the acceleration. So this is the only case where you need to really worry about it. In most of the problems you're going to be able to get a pretty good guess, or you're going to know what direction the acceleration is, and you should know for this one as well. So let's take a look at the weights. This is 10 kilograms. This one doesn't matter. It's a heavy weight, but assuming we're not worried about will it start moving, we're just worried about it moving. It's going to continue to move. It's just one coefficient of friction. We're going to have an accelerating in the system no matter what. So we're not worried about that. So we have mass number 1, mass number 2. This is a little heavier, but notice this one is substantially heavier than this one. It's not going to spontaneously, this weight's not going to spontaneously make it move to the left or the right. It's just going to resist the motion. This one here is going to pull this way, this one's going to pull this way, but it's going to go much more this way. So we know for sure the acceleration is going to be in this direction. Let me write that up here so we know this. The acceleration is going to be in that direction like this. And the acceleration for all three masses will be the same. Now what we do is the same thing we've done for all of our other problems. We isolate each mass. Now that I've done this, I'm going to erase these up here. We may need this space. So we're going to isolate each individual mass and create an equation for a motion for that one. So we're going to start off with this one over here. Draw a little box around that, like that. Here's our green box. M1, 10 kilograms. We're going to ignore the weights till we get right to the end, because you're going to see again, even in this more complex system, you're going to see the same analogous answer fall out as has for all of our previous pulley problems. Let's take a look at this one here and check to see what are all the forces acting on green person here. Well, for one, we have tension going up. Which tension though? Tension 1. It's the yellow tension there. And we have this one going down, which is M1G. Don't forget the specific number for the box. Those are the only forces acting on it. Now we know from Newton's law that the net forces, the unbalanced forces acting on an object, there's no forces acting left or right. That's why we're not worried about that, is going to equal that mass times acceleration. Which mass? This mass number 1, because this is the mass we're dealing with. And what is the net forces on this one? Well, we know first of all that mass times acceleration is going to be upward, which means since we're calling this as positive, the upward force here is going to be bigger. So we'll do that one first. T1 minus M1G. Here we have our first equation right here. Since we've sort of run out of room here a little bit, I'm going to squeeze them in right over here. I hope this light doesn't block your view, but I'm going to rewrite it over here, so hopefully I'll write it big and bold. There we have the first equation. I'll call that equation number 1. Now let's erase all this and see if we can figure out equation number 2. I'm going to skip equation number 2 because it's more complicated. I'm going to go straight to equation number 3 here. Or whatever we call them, doesn't matter what we call them. So here's another equation here. We'll have this here, dashed line, M3 right there. Now let's take a look at all the forces acting on the pink box here. For one, we have this tension. What tension is that though? Whoops, that's tension 2. It's more complicated. And we have this thing acting down, M3G. And again, we know the same thing. The mass of 3 times the acceleration of 3, which is the same acceleration for all of them, is going to be equal to, well, since we know it's going this way, this one's going to be positive. So we take this one first. m3g minus T2. Here we have another equation. I could call this equation 3 or equation 2. It doesn't matter. Let's call it equation 2 for now and rewrite it up here. We'll be rewriting those again. I'm just putting them up there so we remember them. All right, here we are. We've drawn an isolation box, or we haven't yet. Let's draw this isolation box directly around. We're not including the table. So it's just right around the box here. And we look, what are all the forces acting on the box? Well, we know a number of them. For one, this table is going to be pushing upward on the box with a normal force. And also, the box is going to be going downward with m2g. These two forces are going to be equal to each other because it's not indenting the table or the table is not pushing up on it. So we could actually write down normal forces equal to m2g. That gives us a little bit of a tip, a little jump ahead. Now we're going to need other forces as well. Well, there's this one, T2, this one, T1. Now the other one that's sort of a little bit more difficult, I'll use a different color for that. Since friction is painful, I'll use red for it since I used the coefficient of friction as being 0.1. So what direction do we do friction as? Well, we know it's accelerating this way, which means friction has to oppose the motion. It always opposes the motion or the desired motion. If you're pulling on something, friction is going to pull in the other direction, even if the thing isn't moving. So the friction is going to be going in that direction. So we're going to also have this here, the force of friction. That's also going to be acting to the left. And we've got almost everything here. Now, what's the force of friction? It's going to be equal to the normal force times mu. That's the standard definition. In this case, the normal force is exactly equal to m2g. We can plug that in now, or we can plug that in later. But we can create a third equation now. We're going to need some space to be able to do that. Maybe I have enough room right in here. Now we want to find out mass 2 times the acceleration of mass 2. We want to find out what that is. Well, we know it's going to be equal to the unbalanced forces. Since it's accelerating in this direction, we can make T2 positive and putting that first. That's the only thing pulling it. And then what's going to be pulling it backwards is T1, which is this. And also, this is going to be pulling it backwards. It's normal force times mu, or if I want to get more decorative, m2g times mu. So this is equation number 3. I'm going to erase a few things here, just that for now, and transport equation number 3 up here. There you go. Okay, now I can erase this. I'm going to try to leave equation 3 here and here. This is equation 3, just so we can see them all. Now what we have is 3 equations, 3 unknowns, which means we have T1, T2, and A. We want to get all of them, but the easiest thing to do is say, is there a way of getting rid of one of them? Is there a way of unplugging one of them? Well, here we have T2 equaling just A and G. So we could actually take T2, plug that value into here, and the same thing with this over here. So let's just write some of those things out, give me some space to work. So here, if we solve this here for equation 1, we're going to have, I'm just going to write it out so it's not confusing, is equal to T1 minus M1G. Now let's take this to this side. We're going to have T1 equaling M1A plus M1G. This to this side, leaving this on this side. So here we have an answer for T1, which we can plug into here. Right there. And we can do the same thing with equation 2 for T2. I'll change colors for that. Here's T2. M3A is equal to M3G minus T2. I'll move the T2 to this side and this term to this side. So I'll do this slowly. Here's T2. I'll move this to this side. I'm going to leave the equal sign in the same place. I'll have M3G subtracting this, minus M3A. There we go. I've got something here, right here for T2. I can plug that into here. Now I'm going to have a little bit of a mess here to try to keep track of everything. I'm going to try to figure out how to do that. Maybe if I write everything down here to start with, I can do all of that. I still have equation 3 written out, which is very convenient. I'll want to take, now I'm going to have to erase some things here because I'll still have that, but I want to take T2 and plug it in there. So let's do that. T2 plugged in right here, first term. So it's going to be M3G minus M3A. The A's and the G's, my A's and G's start to look very similar, so I have to be careful. Hopefully I don't confuse them. So I'll just put a bracket around that just so that I don't confuse it. Minus T1 which we did right here, m1a plus m1g, that's this term here, and then we go minus m2g mu, this last term here. So here I have all of these terms. I'm going to erase the stuff in the middle and try to rewrite this here, and then we'll collect some terms. All right, I'm going to have you follow me along here. So this is m2a, this is the first term here, is equal to m3g minus m3a. That's this first term. Now here I've got a minus sign here, so I have to be careful. I'm just going to give a couple of lines here. Minus m1a, there's a double negative. I mean a negative on this and this, m1g. I've done that one. And then this one over here, I've got one more, minus m2g mu. I have all of these terms, I'm hoping. Now notice, I'm going to take all of the terms with acceleration in there. That one, and this one. And notice this one here, I have a little more space here. Now here we have, this is m2a, this is m1a, but it's a minus sign. So that would be plus if I move to this side. This is m3a, it's going to become plus. So it's going to be m1 plus m2 plus m3 all times acceleration. That's going to be this term, and this term. I move them all to the left, is going to be equal to all these other terms. What do I put first? m3g. And then I'm going to subtract this one, minus m1g minus this one, m2g mu. Next step, m1 plus m2 plus m3, divide everything by that. I'm going to be left with acceleration equals these three terms, m3g minus m1g minus m2g mu, all over m1 plus m2 plus m3. This is a g here and this is a mu. And notice here, this may have seemed sort of convoluted or difficult. Part of it was the space I have available, but notice here the acceleration of the system is equal to this mass, which causes the acceleration, minus this one that slows it down, minus the friction on this one, which is m2g mu. So these two resist, provide a negative force, these provide a positive force. So this is the net force, and this is the net inertia of the system, and that's what the acceleration. If you're super clever and you have this exam question, you could almost guess this. Boom. Now we can plug in those numbers and we can get a value for the acceleration. I'm just going to quickly do that offline so that I don't bore you with plugging in all these numbers. I'm just going to write them all up here, and then I'm going to do a quick calculation for you so that the video doesn't become too long. So here I wrote everything out, and I'm getting 0.6 meters per second squared as the acceleration. Acceleration equals 0.6 meters per second squared. If you notice up here, it's 25 times g minus 10 times g minus 80, which is this big mass, times mu, which is about 8 times g times 9.8. So that's subtracted on top. Here's the total masses, and you get an acceleration. Now, how do you find the tensions? Well, we had previous equations for the tensions. I've erased some of those, but I can write them back up here in 2 seconds. Here's the equations that I had before, just combined here. You can do that. You can go back and check the equations as well. So just for speed, I'm putting this up here. M1, A plus G. So the tension here and this one over here is going to be this, since this is rising upward, it's going to be more than just simply this mass times gravity here. It's also having to do with the acceleration. And this one over here is going to have a tension in this rope reduced by the fact that it's accelerating downward. So that's how you get these. I got 104 newtons and 230 newtons for these different tensions, tension 1 and tension number 2 over here. That was a little bit of a longer problem, and if you want to pause this one, go back to the beginning, look up the problem, see if you can just freeze it on that and solve the whole thing. If you can solve this one, you can probably solve practically any problem that you're going to have in the pulley, tables, inclines, and stuff like that, as well as friction. This one adds the complication of friction as well. But I just wanted you to see how similar all of the answers look with regard to the equations once you get the acceleration sorted out without plugging in the actual numbers. If that helps, like and subscribe, and I will see you in the next video. Bye-bye.